Okay, so we are still discussing the area problem. So last time I already motivated the problem. So what we want to do is we have a given function which is assumed to be non-negative, and we want to compute the area which is below the function and above the x-axis. Actually, it's, first we have to define it. So actually, it's not a problem of computing the area. It's a problem of defining the area. Now, maybe let's start by looking at some example. So let's choose a very easy function, f of x is equal to x squared, just to see how we are going to, or what is a good method to define the area. Now, let's assume we look at the function on the interval 0, 1. Okay, so we have our function maybe looks like this here. So actually, it's not important. And what we want to do is we want to define this area here. So we want to find the definition of this area. Now, as I have explained last time, so normally in order to define areas, what you do in high school, you first define the area for a rectangle. Then you extend the definition to the area of a triangle. And if you have more complicated domains, what you normally do in high school is you divide it into either triangles or rectangles, and then or also circles, and then compute the area of the domain as a sum of the areas. So for a general area, we will use a similar approach to define the area. So we will inscribe, because we know how to compute the area of rectangles, so we will inscribe rectangles, and we will approximate the area by a sum of areas of rectangles instead. Now, of course, there are several different ways how to inscribe rectangles. In the sequel, we are going to use the following method. So we divide the interval from 0 to 1 into subintervals. Just for convenience, we assume that all the subintervals have the same distance. Okay, so for instance, if you divide it into 4 parts, you have here 1 over 4, then you have here 1/2, then you have here 3 over 4. I should erase this. Okay, now, you have here the function values for those points. Okay, and you, for instance, in every subinterval, you can take the left endpoint. Then you have here one rectangle. Here you have the second rectangle, the third one, the fourth one. And what you're going to do is, okay, we compute the area of the sum of those rectangles and use this to approximate the area which we want to define. Okay, so in this case, because here we are on every interval we use the left endpoint. So this is normally called, or our textbook calls it L4. Okay, so here if we compute this sum, but strictly speaking, we have 1 times 0 square plus 1 times, because 1 is this length here, and the height is given the function evaluated at the left endpoint. So 1 over 4 square plus 1 times 1/2 square plus 1 times 3 over 4 square. And you can compute these values, or for this choice of the subdivision, what you get is 0.21875. And of course, you could also use a different way to approximate the given area by rectangles. Namely, you do not choose the left endpoint, but you choose instead the right endpoint, which our textbook calls R4. It's just the same sum, but now instead of looking at left endpoints, you choose right endpoints. So in this case, you have 1 times 1 over 4 square plus 1 times 1/2 square plus 1 times 3 over 4 square plus 1 times 1 square. And if you compute this, then you get a similar approximation 0.46875, and you see that actually L4, okay, for this special function will be a lower bound of the area we want to define, and R4 will be an upper bound for the area we want to define. So if we denote the area by, let's say, A, then we see that A must be larger than 0.21875 and smaller than 0.46875. Okay, but if you choose a function which is not increasing or decreasing, it's not necessary that those approximations are either give upper or lower bounds. They can also give something different if the function is doesn't have a monotonic behavior. Now, it should be pretty clear how to define the area. Namely, what we are going to do is we make this subdivision here smaller and smaller. So we divide into more and more subintervals, which means we approximate the given area by more and more rectangles. And we use, again, the sum of the area of the rectangles in order to approximate that. So if we carry this out for a couple of choices of the number of subintervals, you find a table, the corresponding table in our textbook. So I just want to copy it on the blackboard just to see some a basic fact about computation of areas. So here we use the 4 subintervals. Now if you use 10 subintervals, you get 0.285000, and here's 0.385000. One more 0. Okay, then we use 20 subintervals, and again we compute the corresponding approximation by choosing once left endpoints and the second time right endpoints. So here we have 0.3087500. Here we have 0.3587500. If we choose 30, we have 0.3168519. So let me just copy the whole thing. Now 50, 100, and 1,000. Okay, and here we have 0. Okay, so if you look at this data, okay, because assuming that we do not know what the right value is, okay, so if you look at this data, you might get the impression, okay, it seems that because this is always a lower bound, this is always the upper bound, so it seems that the lower bound is getting larger and larger, and the upper bound is getting smaller and smaller, and we actually approximate a value which we could from this table, from the data conjecture, is 1/3, which of course you know is true for this area. But you see here something already which is quite interesting. If you look at this data, what do you observe? What do you observe if you look at this data? Actually, if you assume we do not know the right value for the area, okay, then in this case we do not know whether this sequence ln really converges to something. Now, the rule which we normally use if we do such computations in so-called numerical mathematics is, okay, if we do not know the right value, then we assume all the digits which do not change anymore are correct. Okay, this is not really a theorem, but this is something we always use when doing numerical computations. Now you see, okay, if you apply this rule, you see, okay, from the second computation on, this digit does not change, so it should be correct. Okay, by this rule. But you see, for the third digit, okay, here we have 5, 0. Here it still changes. It still changes. We actually, even if we divide the subinterval here into 1,000 subintervals, we cannot make sure that the second digit is correct. Okay, and if you look at this data, okay, you similar observe. You could conclude that the second digit here is correct because it doesn't change. But maybe this is because you have just computed two data, so maybe it's not correct. You have maybe to do more computations, but you can be pretty sure that the first digit is correct. So what you observe from this data is using such a numerical method to approximate the area. Okay, the speed of convergence is very, very slow. You have to divide this interval into 1,000 subintervals. Okay, and you still do not get a very good approximation. Okay. This is important for numerical computation of the area once we have defined it. So this is observed for quite a lot of similar problems. So normally the computation is, if you just do it numerically by really approximating by rectangles, it's always the speed of convergence is always pretty slow. But from this table, we still could guess, okay, that the way we are going to define this area is 1 over 3, just because of the reason, because this sequence seems to tend to 1 over 3, and this sequence seems to tend to 1 over 3 as well. So from this observation, it seems it makes sense to define the area as 1 over 3. Okay, this sequence converges to 1 over 3. Indeed, it's not complicated to prove. So, for instance, if we look at Rn, okay, so for general n, here we use the right endpoint to evaluate. So we have 1 over n, which is the length here of the interval, times. Overall we have n rectangles, and every rectangle has the height I square. I square, I over n square. Okay, and if we want to find out whether this sequence for n tends to infinity converges, is pretty easy, because we can write this as 1 over n to the cube, and then we have the sum from 1 to n I square. And I guess in high school you have learned how to sum this. Maybe you have memorized the formula. I have never memorized the formula, so I have to look it up. Okay, so here you have n times n plus 1 times 2m plus 1 over 6 n to the cube. Okay, and you see, if you look at this expression as n tends to infinity, okay, indeed you see this here will tend to 1 over 3. Okay, which verifies our observation here. Now, this is for the for Rn. As for Ln, actually those two are pretty similar. Okay, the only difference between those two is that here you have the last term. Okay, whereas Ln does not have the last term, because the first rectangle has always area 0. So the only difference between Rn and Ln is the last term, but the last term is 1 over n, which tends to 0 as n tends to infinity. So Ln will also tend to 1 over 3 as n tends to infinity. Okay. So because Rn is equal to Ln plus the last term, okay, you see that the limit of Rn as n of Ln, sorry, as n tends to infinity is equal to 1 over 3 as well. And from this observation, okay, we are going to say, okay, it seems to make sense to define this area. This is not a computation. This is not computing the area. This is defining the area. So from this computation, it seems, okay, it makes sense to define this area as 1 over 3. And we will use the same approach for more general functions. So whenever we have a function and we have to define the area below the function, what we are going to do is we look at the subinterval from a to b. We divide it into subintervals. On every subinterval, we choose, for instance, the right endpoints in order to construct a rectangle which is going to approximate the area on this subinterval. Then we compute the area of the rectangles instead of the area below the function on the subinterval, sum all those areas up, and let n tend to infinity. And if this limit exists, then we say the area exists, and we define it by using this limit. Okay, so you see, you have here, there are several questions here you might ask. For instance, okay, this seems to be quite random, okay, that I divide the subinterval from 0 to 1 into subinterval, the interval from 0 to 1 into subintervals which all have the same length, okay? So maybe one question you can ask, okay, if you make the subdivision such that the lengths of the interval are not necessarily the same, okay, is it still true that the limit if you just look at the largest length and let the largest length tend to 0, so you make the subdivision finer and finer such that the largest length tends to 0, but not necessarily all the lengths are the same, okay? Is it still true that the limit, for instance, for this function here, of the corresponding sum of the rectangles exist? And indeed, it can be proved, yes. No matter how you do the subdivision, even if the intervals do not have all the same lengths, but you have to assure that the length of the largest interval tends to 0, then it still can be proved that the sum of the area of the rectangles converges, and it converges actually, of course, to the same limit. It's 1 over third, something which should certainly hold if this definition of the area should make sense. This is the first thing. And the second thing is, okay, we always chose, okay, either left or right endpoint of the subinterval, but of course you could also choose some sample point inside the subinterval and use this sample point, evaluate the function at this sample point and use this as height, okay? And again, for this function, if you do this and you write out those sums, again, you can prove they all do converge and all do converge to the same limit. Okay, so this leads to the definition of the area for a function which is non-negative of the area below the function and above the x-axis. Any questions to this? Okay, so if we have a general function f of x being larger or equal than 0 and on an interval a, b, okay, so for instance, let's say this function looks like, okay, so for instance, this function, now what we do is, okay, we again divide the interval ab into subintervals. So this should be here x1, this should be x2, a is equal to x0, the last one is equal to xn, we have here xn minus 1. Okay, and then we choose, in every subinterval, we choose some sample point. So we have, first we have this subinterval, then we have this one, here we have this one. Okay, in every subinterval, we choose some sample point. Okay, so for instance, let's choose this one, which serves then as the height of the rectangle. And then we approximate the area below this function, okay, it's the sum of the areas of the rectangles which have this given height here. Okay, so this one. No. And then we let the subdivision get smaller and smaller, so n tends to infinity. So just in order to fix some notation, the length of every subinterval is equal to b minus a over n. So this means that x0 is indeed a, x1 is a plus delta x, then x2 is a plus 2 delta x. Okay, and we go on like this, and then xn minus 1 is a plus n minus 1 delta x, and finally xn is equal to a plus n delta x, which is equal to b. And we choose a sample point. Let's call all those points here, which we chose in every subinterval, xi star. So this is a sample point in the I subinterval. Then what we can do is, okay, we can approximate the area by the following sum. So the sum I from 1 to n, f evaluated at the sample point, which corresponds to the height of the rectangle, which approximates the area above the interval from xi minus 1 to xi times delta x. And if this limit here exists, and existence here once more means, because this limit, this is not just one limit, okay? This limit depends on the choice of the sample points, okay? For different sample points, for different choices of the sample points, you get different limits. So what we have to assume is that all those limits, no matter how we choose the sample points, all do exist. Okay, if this is the case, then we define, if they all exist and are the same, then we define the area below the function of f as the value of this limit. Okay, so actually here we have a good question, okay, namely, okay, for which functions do all those limits exist? Okay, now our textbook mentions always without proof. That's why subsequently we will always consider f to be, most of the time we will consider f to be a continuous function, so it can be proved, but this is proved in other courses on higher mathematics. But it can be proved that if f is a continuous function, then no matter how you choose the sample points, those limits, all those limits exist and all do have the same value. And in this case, so if f is a continuous function, this definition of the area makes sense. Or in other words, for continuous functions which are larger or equal than 0, the area below the function and above the x-axis is defined. Okay, so in our textbook, you always see that, for instance, for this definition, which you find in our textbook, you see that the author assumes that f is a continuous function. Only for continuous function, the author makes this definition, because the reason is because only for continuous function, all those limits exist and have the same value. Okay, and as I have mentioned, it also sometimes normally in textbooks on higher mathematics, you find a more general definition, namely, it's not necessary to make the subdivision of the interval AB such that the length of every subinterval is the same. Okay, you just have to. You can also choose different lengths, but if as n is getting larger and larger, you have to ensure that the largest length tends to 0. Okay. If you choose the subdivision like this, again, it can be proved. All those limits exist and have the same value as this one. Okay, so any questions to this? Now, we already saw one example where we were able to compute the area, namely f of x is equal to x squared. In this case, we were able to write down this sum and to take the limit. But if you look at other simple functions, okay, this computing such limits very quickly gets very complicated. For instance, choose the function f of x and the interval 1 to 2. Okay, so also this here. So in this case, if we plot the situation, so our function, so only from 1 to 2. Okay, so our function looks like this decreasing. So it looks like this here. And what we want to do is, okay, we want to compute this area. Now, if you use this, if you use the definition, okay, so what you have to do is, okay, you look at the sum I from 1 to n. For instance, let's choose as a sample points. Let's choose right endpoints. Okay, so you have you divide the interval into intervals of length 1 over n. Okay, and then you have 1 over 1 plus, because you start from 1, I over n. Okay, and you have to figure out, okay, what is the limit as n tends to infinity of this sequence. Okay, in order to compute the area. Now you see it. Okay, you can write this as. Okay, if you like, you can write this as maybe a little bit easier. Okay, or if you avoid the sum notation. Now your problem becomes, okay, how to compute the limit. Any question? I didn't forget this one because I multiply everything with n, and then I have here an n, so this cancels. Okay. Now the question becomes, because if you wanna compute the area, okay, we have to compute the limit. Okay. But who knows how to compute this limit? So you see already for this very easy function, evaluating this limit, not easy. Okay. Because the answer, as you might know, is ln 2. Okay. But we cannot, unless we have some clever idea, we cannot compute the limit from here, okay? Observe here, something which you have to observe is n tends to infinity, okay? You see that every term tends to 0, but this doesn't mean that the sum tends to 0. Okay, this is quite crucial here, okay? The reason is because as n is getting larger and larger, the number of terms is also getting larger and larger. So you cannot just say, okay, the limit of this sum is the sum of the limits. Okay, if you would be able to do this, then it would be 0. But in this case, the answer is ln 2. So we see here that this definition is quite awkward, okay, because it's, of course, it defines the area, but even for very easy functions, okay, it's not clear how to evaluate the corresponding limits, or in other words, it's not clear how to compute the area. So one of our main problems is, okay, is there a good way an easy way to evaluate such limits? Okay, and indeed there is an easy way which we will find maybe today or next time on Monday. Okay, so this is the main thing is, okay, this is the definition of the area of a positive function or non-negative function below the function and above the x-axis. And our first major problem is, okay, how to compute the area, or how to evaluate this limit. Because if even this function is complicated, okay, this easy function, you can, if you take another function like arctangent, okay, then you will end up here with something which is arctangent of I over n, okay, and the sum. This will be even more complicated. So there is obviously a need for finding a good tool how to compute easily such limits. Now, this is the first classical problem which I wanted to discuss. So the area problem. This is a problem which was arising from mathematics. A problem which is quite similar, related to this problem, is the so-called distance problem. Now, assume that. So you find in our textbook. Assume that. actually, I should first maybe say what the distance problem is. Now you have given the velocity at certain time points, and you do not know the distance traveled, and what you have to compute is the distance traveled. Now, this problem is very easy if you assume that the velocity is constant, because then you just apply the time length with the velocity and you get the distance. But if the velocity is not constant, if the velocity is changing, you get a similar problem. Of course, from physics or from high school, you know how to solve this problem. But as I said, we assume here that we haven't defined yet the integral. Okay, so you have to look at the problem from this angle, because this is very essential now, because we will see that the distance problem and the area problem are pretty similar, but from the distance problem you can learn something which you cannot learn from the area problem. Now, I will emphasize this in a few minutes. So you see in our textbook there is an example where it's assumed that the odometer of our car is broken, so you cannot read off the distance traveled. So what you do is you measure the velocity, or you look at the speedometer after every 5 seconds. So assume that we observe the velocity over a period, over a time interval, which are the first 30 seconds. So at the starting point, we look at the speedometer. After 5 seconds, we look at the speedometer. After 10, after 15, after 20, after 25, after 30. Okay, so because your odometer in your car is broken, okay, so you do not know the distance traveled. So, but you still want to understand, okay, in the next 30 seconds, okay, what is the distance traveled? So, one way to easy way to solve this problem is, okay, at the beginning you look at the speedometer, you read off the velocity. After 5 seconds, again you check the velocity. You write this data in a table. So here's the velocity. The velocity in meter per second. In our textbook, you'll find feet per second, but I'm not used to feet, so I use meter per second. So you have here 25. Here you have 31. Here you have 35. Here you have 43. Here you have 47. Here you have 46. And here you have 41. Okay, so actually, because I changed it to meter per second, so for instance, this would be rather fast, something like 170 kilometers per hour. You are not allowed to drive that fast unless you're in Germany. Okay, we do not care about this. We assume we drive in Germany, then we are allowed to do this. Now, you can easily approximate the distance. Okay, so by assuming that, for instance, over this 5-second time period, okay, you assume, okay, actually the velocity was constant, which is of course not true, but just in order to approximate the distance. So what you do is you multiply 5 with 25, then over the next 5-second time period, you assume, okay, this is the velocity, and you go on like this. Okay, so like this, you can obviously approximate the distance, which is because we drive rather quickly, so the distance we travel in 30 seconds will be rather a lot. So it's almost 1 kilometer. Now, so this is one way to approximate the distance traveled. Another way to approximate the distance traveled, because we assumed here always that over a 5-second time period, the speed was, or the velocity was constant, and we always chose the left endpoint. But of course, you can also choose the right endpoint. So you have then 5 times 31 plus 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 46 plus 5 times 41. Now this will give you, of course, another value, but which is close to this value. Meter. And if you want to make this estimate of the distance more precise, what you do is you just use here more sample points. So for instance, here we divided the interval into 7 subintervals, but you can, for instance, you use 14 and so on, into 6 subintervals. But for instance, you use 12, so you look also after 2.5 seconds, after 7.5 seconds, and so on. You read off the velocity, and you do the same approximation. You get a better approximation. And you see already from here, actually, what we are doing is you look at the velocity function, okay, and you approximate the area below the velocity function and above the x-axis. It's just the same computation as we have done, okay, for defining the area f of x is equal to of f of x is equal to x squared, which is below this function and above the x-axis. So you see here you will encounter similar sums. Okay. So in more general, okay. So more general, if you have given a velocity function, okay, which is assumed larger or equal than 0, so you move forward. And the t is over some time interval. Okay, so again, in order to approximate the distance traveled, you divide the interval into subintervals, as we have seen. So the delta t is then b minus a over n, for instance, n subintervals. And you define time points, ti, which are plus I times delta t, where I is from 0 to n. And then in every time interval, you can, more generally to what I have done, because the table I just showed you, I just looked at the beginning of a time interval and the end, but you can choose a sample point in the middle. So you choose sample points in the ith time interval. Okay, and using this data, you can approximate the distance. Okay, as the sum I from 1 to n, the velocity at the sample points times delta t. Okay, and if you let n tend to infinity, so actually the same limit occurs. So if you let n tend to infinity, here you should recognize this problem is a little bit different from the area problem, because for the area problem our goal was to define the area, but here the distance is something you can measure. Okay, so this just gives you another way to measure the distance. Okay, but actually because the limit of this sum, okay, is a mathematical object. Okay, so you actually have to prove that the limit is equal to the distance. Okay, so here you have to prove something. Okay, so the problem is a little bit different. Okay, but so our guess will be that t is equal to, so the distance is equal to the limit as n tends to infinity, sum I from 1 to n v of t at the sample point times delta t. And this is something we have to prove here. Okay, because this is another way to, you could say from the physical context, it's clear that those two should be the same. Okay, but the limit is a mathematical object. Okay, so if you, in mathematics, of course, you have to prove this. Okay, but this is something, if you look at this situation, okay, this gives you something very interesting. Okay, and something which is very unexpected. Namely, you see that for the distance, we actually have an interpretation. Namely, the distance, in terms of the velocity, we know that the distance is the antiderivative. Okay, so from this here, you can guess that in order to compute such sums, areas, okay, the notation of antiderivatives might be helpful. Okay, so this is something you see here. Okay, Now, but if you forget about this physical context, okay, if you go back to the mathematical question of computing areas, okay, it's not clear that the area problem, as we have defined it, has anything to do with the tangent problem. Okay, they seem to be rather different. The area problem was, okay, you have a given function which is now negative, compute the area below this function. The tangent problem was, okay, how to define the tangent at the given point of the function. It doesn't seem to, it's not so obvious that the two are related, okay? But here from the physical situation, okay, you see actually they seem to be related very closely. Namely, if you want to compute areas, okay, what you have to understand is antiderivatives of the given function. Okay, this is very remarkable and very surprising, in some sense, very surprising relationship. And next week on Monday, we will prove that this is indeed true, so that there is indeed a very close relationship between differentiation and integration. Or I should say, we haven't defined the integral. So between area, computing of area, between the area problem and the tangent problem, and because those two problems are the most important, or are the origin of calculus, so the theorem which we are going to prove on Monday is, of course, the most important theorem in calculus, and it's called the fundamental theorem of calculus, because it tells you, okay, there is indeed a connection between the area problem and the distance problem. And this will also help us, between the area problem and the tangent problem, this will also help us in order to compute such limits. So this is something you should understand in order to be able to grasp what I'm doing in the sequel. Okay, so any questions to this? Okay, so this already here, once more, this physical problem here already paves the way for everything we are going to do in the sequel. Namely, from here we will guess, okay, that if you compute the area, okay, the area will be an antiderivative of the. So if you compute the area where the right endpoint is a variable, okay, then this will be an antiderivative of the function for which you compute the area. This is one thing we are going to prove. And antiderivatives from here, you see this as well, are helpful in order to compute such limits. It's a very remarkable observation. Now, because we saw that this limit, which I just erased, seems to show up in different contexts. So we saw for computing areas, we encounter this limit. Computing distances, we encounter the same limit. So it seems to make sense to give this limit a name. And you know already how this limit is called from, I guess, maybe not from high school. So we use the same notation. So we have a given function f, which is assumed to be continuous. So f continuous on AB. This is what we need, as I have explained, in order to ensure that this limit here exists. And as always, the delta x is b minus a over n. The xi is a sample point in the i's interval. And xi is equal to a plus I times delta x. Okay. Now, we saw already that this limit, okay. Now, we do not necessarily assume that f is non-negative. So we consider the general situation where f might be positive, negative. We saw that this limit here, okay, seems to show up in different applications, namely computing areas, also computing distances. So as I have explained, it makes sense to give it a name, and this name is the integral from a to b f of x dx. So this is just a name for this limit here. Now this integral, as explained in our textbook, is called Riemann integral. So this is called Riemann integral. It's double n or 1n. I will never memorize this. Riemann, okay, double n. The reason why this integral is called Riemann integral is because there are many more integrals, not only this one. You will learn other integrals in courses on higher mathematics. So this is the most simplest integral, so called Riemann integral. Now, this sum here is called Riemann sum. Just for the notation, this function is called integrand, and a and b are called lower limit and upper limit. We will see that actually the integral is not only useful. So in some cases we can interpret this as an area. Namely, we saw if f of x is larger or equal than 0, then the integral is an area. Yeah, actually, we need also that b is larger or equal than a, because for this definition, we do not necessarily need that b is larger or equal than a. But for this special situation, we know, okay, the integral represents an area. We can think about the integral as an area, but we will also see many other applications, many other situations where the same limits will occur. Okay, so the integral can also be used for computing lengths of arcs and volumes of solids and so on and so forth. We will discuss this. So then we understand that it really makes sense to single out those limits and give them a new name. Now, the reason for this sign you maybe have already heard in high school, because it's essentially just taking this here and replacing the sum here by this here. So it also represents summing. Okay. But since the subdivision of the interval is getting finer and finer, so you sum many, many terms, okay? And you just rewrite this symbol. This is the basic reason behind using this symbol here. You just rewrite this symbol here slightly. You replace the sum by the integral and delta x by dx because it's getting smaller. So that's the only reason. Now. If the function f of x is not necessarily satisfying this condition here, if the function is positive and negative, then actually what you get is an area as well, but the parts which are above the x-axis are counted positive. The parts below the x-axis are counted negative. So what you get, you can say, is a net area. So this symbol will help you to sum up all the areas where all the areas above the x-axis are counted positive and the other ones negative. So also in the general situation, and b is larger or equal than a, this symbol here can be interpreted as an area. This is a little bit different maybe from high school, because in high school you define this symbol as an area. But we define here the area as this limit, and this symbol as this limit. Okay, so any questions to this? Now, maybe I should say that the textbook mentions as well that you always see this assumption f is continuous. You should keep in mind that the reason why we have this assumption is that for this assumption it can be proved that all those limits here exist and are the same. Okay, but we are not going to go into details and prove this. Our textbook also mentions, actually this is true for also in a more general situation. So not only for continuous function, all those limits exist and are the same. For instance, if f is not continuous at some points, but doesn't behave too badly, so essentially what you can, for instance, you can allow a finite number of jumps. If f has a finite number of jumps in this interval, so a finite number of jump discontinuities, then it still can be proved that this limit always exists. And for independent of the sample sequence, of the sample points, is always the same. Okay, so actually continuous is not the most strongest assumption under which these limits here exist. And in courses on higher mathematics or in textbook on higher mathematics, you can find exactly, you can find theorems which exactly tell you which function, for which function f do all those limits exist and are independent of the choice of the sample points. But we are not going into such details because this would take too much time. Okay. Now, any questions to this? Now, as I have explained already, our first major problem, and from the physical situation we already have an idea how to attack it, but our first problem is essentially, okay, how to compute, for a given function, how to compute this symbol, because the only method we have so far is really to go into the details, to write down this sum here, and to try to let n tend to infinity and to figure out what is the limit. And we saw already for some examples, even easy examples can be pretty complicated. Maybe it's worth it to check out some examples just to appreciate more what we are doing in the sequel. So let's really go into the details in order to solve some examples. In our textbook, you find or let's keep this example here. So you find that actually we have already seen that for this example here, the Riemann sum does not look too bad. So in this case, the reason why we are able to compute this limit essentially is because we can sum up. So we can take, of course, we take out 1 over n squared, and the rest we can sum up. We have a formula. That's the reason why we can compute this. You know that there are similar formulas for instance, for this one, there's a similar formula. And so on. For instance, if you want to replace the x here by x to the cube, okay, then you have a similar sum. Maybe let's look at this example. Okay, then you have a similar sum, and then you have to use such a formula. So in this case, you have limit n tends to infinity 1 over n to the 4. Now the sum here is exactly this one, so you plug this in, so you have n squared n plus 1 square over 4, and this limit indeed is 1 over 4. Okay, so also in this case we are lucky because we know this formula, so we can compute the limits, hence we can compute the integral. Now, if you look at other examples which are slightly more complicated but also manageable. So for instance, f of x is equal to e to the minus x, where x is on the interval from 0 to 1. Okay, so in this case, you have the integral from 0 to 1, e to the minus x dx. Now you see that, okay, so using the definition, this will be the limit as n tends to infinity. Now, every subinterval has length 1 over n, and then you have the sum I from, for instance, we can choose, here I chose right endpoints, but let's maybe choose left endpoints, e to the. Now, because I just mentioned this example because our textbook claims this is complicated to compute. This is not complicated to compute because you know from high school. Also this example is manageable. Our textbook uses this example in order to demonstrate that computing integrals, that computing such limit can be complicated. But I don't think that this is a very good example because you see that, okay, so this is something which you have already summed up in high school. Okay, so this here is the limit. N tends to infinity. And now you know that there's a formula in order to sum this up here. So what you get is e to the minus 1 over e to the minus 1 over n minus 1. Okay, so you are left in computing this limit here, but you see that this is a constant, so you can take it out. Okay, and you see that that what remains. Okay, it's maybe better to write this as 1 minus e to the minus 1, because then what remains is minus 1 over n over e to the minus 1 over n minus 1. Okay, so 1 over the derivative of e to the x at 0. Okay, because this what you see here is a derivative. So you have 1 minus e to the minus 1, 1 over the derivative of e of x evaluated at x is equal to 0. Okay, so 1 minus e to the minus 1. So actually, also this integral is not using the definition, not too complicated. Okay, because our textbook once more claims that this is a complicated sum to evaluate. It's not true. Okay, so any questions to this? Now, maybe let's look at a more challenging one. So we see that, what we essentially observe is that it seems every function we need a new idea, because here for this function e to the minus x we had to sum up, okay, e to the minus 1 over n to the I, and we know a formula for this. For if we have something like x to the integral over x to the cube, okay, we have a different sum over I to the cube. So essentially, always what we encounter are summing up some quantities. But in order to prove such summation formulas, okay, for this one it's quite easy. Maybe the sum over I to the cube is a little bit more challenging, but others might get quite tricky. So for instance, let's look at the cosine. Okay, now, and let's say the interval is 0 to pi half. Okay, now, if we want to compute the integral from 0 to pi half cosine of x dx, okay, so by definition, this is the limit n tends to infinity. Now, we divide the interval into n subintervals, so this is the length of a subinterval, and then we have the sum from 0 to, let's say we use left endpoints, the cosine of pi I over 2n. Okay, now our question becomes how to sum this here. Okay, this is not so easy compared to the sums we have encountered before. Now, this is something you can first give it to Maple. Let's check whether Maple can do it. Okay, you give Maple, for instance, this sum, and tell Maple, okay, sum it, and Maple indeed will give you an answer. Namely, this is equal to minus 1/2 cosine nx minus 1/2 sine of x sine of nx over cosine of x minus 1 plus 1/2. Okay, so this is the answer I got from Maple. Okay, so once you know this, okay, now the remaining thing is easy because now you plug everything in. So this integral okay, so we have still the limits. So we look at our x here is pi over 2n. Okay, so if we look at this one is 0, so we can forget about this one. Now we have the last one, which is 1/2 1 over 4n pi, because we still have this here, minus 1/2, and this is the sine of pi over 2n. Okay, and here we have the sine of pi over 2n, so pi half, which is 1, so forget about this. And here we have the cosine of pi over 2n minus 1, and we have also this here, pi over 2n. Okay, and we have the limit. Sorry, I forgot the limit. Limits as n tends to infinity. Okay, so the first one is easy. The first one is 0. Now, for the rest, so we have minus. Let's just take out the constant pi over 4. And then we have the limit. So n tends to infinity, so this means x tends to 0. Okay, so we have sine of pi half x over cosine of, we have here another x, cosine of pi half x minus 1. So actually this is 0 over 0. So what we do here is, this is equal to minus pi over 4, the limit, x tends to 0. Now, we write here sine pi half x over pi half x. This will give us here another x squared. And we have here the cosine pi half x minus 1. And we have here pi half. Okay, because we know that this here tends to 1, so we can forget about this. So we have minus pi over 4, and the limit x tends to 0. And what we still have is this one. So this is pi x over, and here we have minus sine pi half x times pi half. Okay, so now you see, okay, if you multiply this here with 2. So also this here is 1. So what do we get overall? Pi half 1. Okay. Now, if you compute the area below the cosine of x between 0 and pi half, okay, the area is equal to 1. But you see from this example, okay, that computing, if you just use the definition, okay, and you try to find the limits of the Riemann sums, okay, which you obtain, sometimes the sums you encounter can be quite complicated, okay, and you sometimes have to solve a complicated problem in order to, a complicated summing problem in order to be able to evaluate the limit. This, for instance, computing this integral, okay, when the definition of integrals or the definition of areas was given first time, for the first time, computing this integral was rather challenging. Okay. Now, on Monday we will learn a tool which makes this computation completely trivial. And from this here, you should appreciate. Okay. On Monday you will see that once we have proved the fundamental theorem of calculus, which will tell us how to compute this symbol easily. Okay, you will see that this is really a very important result, because once you have done this result, you do not have to go into such messy computations. You might wonder, okay, how is Maple able to compute this here? Does anyone have an idea how to compute such a sum? For instance, if you change this to, let's say, L, you can think of course, once you know this, you can prove it by induction, okay? But maybe you can think about it, whether you are able to compute this sum here, to sum it up, okay? You might imagine, okay, if I use some trigonometric formulas, okay, it will be indeed possible to get this result here. So you can try it as a homework, which you do not have to handle in, which is a homework which is not part of the assignments. Okay, so any questions to this? So if you try this, let me know, because I can tell you a very, very easy method to solve it. Now, maybe there is not a lot of time left, but maybe let me just show you one final example, which tells you that because we always now for the examples I showed you, okay, I always chose either the left or right endpoints. Okay, sometimes if you cleverly choose the sample points, okay, some sums which might be or some integrals which might be pretty complicated. I should actually say some Riemann sums which might look pretty complicated can get very easy. Okay. So, also, this is worth it to point out. So, for instance, if you have this one, okay, so you want to compute this integral. Now, okay, you can write this as limit n tends to infinity. Now, again, we divide the interval into subintervals of length 1 over n, and we have the sum. So, for instance, if we choose here, let's say we choose left endpoints, then what we get is 1 over 1 plus I over n square. Okay, so actually this here looks quite horrible. Okay, it's not so easy. Okay, so here a trick, okay, is as follows: you choose the sample points, because actually here I chose the left endpoints. Okay, but you can choose them differently. For instance, here the maybe the major idea, okay, is to choose them as so to choose the sample points as the geometric mean of the right and left endpoint. Okay. The reason why this is a good choice is because you have a square here, and if you choose the geometric mean, it will disappear. Okay, so you have this is the geometric mean of 1 plus I minus 1 over n, 1 plus I of n. Of course, this looks rather complicated, but taking this function into account, it gets easy. So this limit is also the same as the limit n tends to infinity 1 over n, the sum I from 1 to n, and now I choose this here as sample points. So 1 over, because I have to square them, so I have 1 plus I minus 1 over n times 1 plus I over n. Okay, now you see that this is equal to the limit n tends to infinity. Okay, so I can multiply this with n square and take an n square out, so I have n sum I from 1 to n. And then I have here 1 over n plus I minus 1 times n plus I. Okay, now you observe that 1 over m plus 1 is equal to 1 over m minus 1 over m plus 1. Okay, so you plug this in here, so you get this is equal to the limit n tends to infinity. And then you have n times, and this sum you can divide it into two parts. So one is m plus I minus 1 over n plus I. And now you see here something interesting, the telescope. Okay, so if you write down this sum here, so you have limit n tends to infinity n times. And if you write this down, so the first one is 1 over n minus 1 over n plus 1. The next one is plus 1 over n plus 1, plus minus, and so on. And the last one is 1 over minus 1 over 2n. And actually, the middle ones all cancel out. Okay, so you see the middle ones all cancel out, and so on. So only the first and the last remain, which makes the limit very easy. Okay, because you see that it's only 1 minus 1/2. So what you get is 1/2. Okay, so sometimes if you cleverly choose the sample points, it might be indeed possible to solve the corresponding limit problem. Okay. But on Monday we will see a method where we do not have to go into the limit problem, where we use a completely different method to directly solve the integral. And actually, this is something you have learned in high school already, which was maybe the definition of the integral there. Okay, so any questions? If not, then we go on Monday.